Okay, so here behind me is the scary definition of the integral, which I'm going to erase now. And we're not going to use it in proving things, and I'm not going to expect you to know how to use it. It is one step further in terms of complexity and challenging to actually apply. There's no magic, right? If you somehow got used to using the definition of the limit, you can use this as well. And you can open a book, if you're not scared of books, and see how it's used to actually prove things. And I think you should be able to follow. The one thing I hope I did convince you is that even if we know a function is integrable, calculating integrals in terms of writing partitions, finding the Riemann sums, and then taking the limits is something rather complicated, rather tedious. And we want a better way of doing it. I'm going to leave this on the board because this is our standing assumption throughout our discussion of definite integrals. And what I want to do now is write a bunch of theorems, a list of theorems. I'm going to discuss, I'm not going to prove them, maybe one or two briefly, but I'm going to discuss for each one the intuition behind them. I'm going to relate them to the intuition which stems from the drawing, from the way we intuitively think of integrals. And the first theorem we had, I'm reminding you, is the one over here, that if a function is continuous or monotone, even piecewise, then it is integrable. Tell me when you feel that I actually provided an alternative way of calculating integrals. Do you agree that this statement tells you that you know many, many, many integrable functions, but it still gives us no alternative way of calculating them? Okay, so if I ask you, what's the integral of x squared between 0 and 1? Okay, you know it's integrable, but what is the integral? You still have to go back to those Riemann sums, right? So tell me when you feel that maybe I just provided a tool for actually calculating. Hint, it's going to take a while. Okay, so let f from AB to R be bounded. Theorem, and I'm just going to enumerate the various parts and call all of them one theorem. Okay. In fact, sometimes in some of these, we're going to have an f and a g. So when we have an f and a g, I'm going to assume both are from AB to R bounded. So 1. Theorems. THM stands for theorems, too. Okay, 1. So suppose we have an integrable function on AB. F is integrable. Oh, wait, no, I have to write that. Okay, sorry. If f is integrable on AB, then it is integrable on any CD which is contained in AB. So whenever you take a subinterval, it's going to be integrable on that subinterval as well. Clear? Okay, so if somehow the magic of those Riemann sums converging to the limit, to the integral, happens on a bigger interval, the same magic is going to happen on a smaller interval. So that's the first theorem.
What does that say with that thing?
This means contained. We met this notation previously. Okay, and when I write like this, I'm saying contained or equal. Okay? Part 2. Part 2 is called additivity. Additivity. Says the following. It's kind of the other direction to this. If f is integrable on AB, and BC, so suppose you know it's integrable on these two intervals, then guess what? It is integrable on AC, and moreover, the integral from A to C of f, I'm going to skip writing f of x dx every time just to make it more, the formula is more concise and more easy to remember, equals the integral from A to B of f plus the integral from B to C of f. Good? And each time you write something like this, in your mind, you should draw a little picture. Sometimes I'll draw them for you. So here's the little picture going along with this. This is the intuitive picture. It's not a proof. The formal proof, no choice. You have to go through those epsilons and deltas and partitions and norms and whatever. But the intuitive picture, that you can add these intervals. So here's f, and you know it's integrable on a, b, and you know it's integrable on b, c. The statement is it's going to be integrable on the entire interval, and intuitively, the area under the graph here plus the area under the graph here is going to equal the area under the graph on the entire thing. Do you agree that this is as intuitive as possible at the intuitive level? Yes? That's this statement. So that's the second theorem. Do you see already a way to calculate? To calculate. Are you making jokes? I'm the one that makes jokes in this class. Okay, no, right? But good. I like funny people. Okay, still no method of calculating in these two theorems, right? Let's try some more. Number 3. Okay, number 3 is called linearity. Linearity. If f and g are integrable on AB, if both are integrable, and take two constants, call them alpha and beta, two real numbers, alpha, beta, and r, then alpha f plus beta g is integrable, and the integral from A to B of alpha f plus beta g equals alpha times the integral of f from A to B plus beta times the integral of g from A to B. Okay? Try on your own, I'm not going to do it for you this time, to doodle some pictures and see if you can intuitively agree to this fact. That if you add two functions or multiply a function by a scalar, the area under the graph is going to be the scalar times the area under the graph of the original function. Okay? When you add two functions, the area under the graph of the sum is the sum of the areas under the graph of each one of them. Okay? And if you want to challenge your intuition a bit further, try to see why this intuitively works out, even for functions which are not necessarily positive. Okay, so alpha can be -5. See why it still works intuitively. But remember that when you have a function that's not positive, it's minus the area above the graph rather than the area under the graph. Okay, so this is linearity. Still, no method of calculating, right? Just nice to know facts. 4. If f and g are integrable on AB, integrable is, int dot is short for being Riemann integrable. Okay? Somebody asked me during the break, there aren't two notions, one of being integrable and one of being Riemann integrable. It's the same notion. Okay? In short, int. Okay? So if both are integrable, then f times g is integrable on AB. What's important in number 4 is that there's no and. There's no formula for the integral of the product. So don't try to invent one. In particular, it's not true that the integral of f times the integral of g equals the integral of f times g. That's false. Okay? Okay. Number 5. Maybe let's take a new board. Number 5. If f is integrable on AB. Ooh, I'm starting to be sloppy. Sorry. On AB, then so is the absolute value of f, and there's no formula, but there's an inequality. The absolute value of the integral from a to b of f, so the absolute value of the integral is less than or equal to the integral of the absolute value. Let's see why this is reasonable in terms of intuition. So, of course, if f is positive, there's going to be an equality here, and the statement is rather not interesting, right, for a positive function. When the function is not positive, here's a function that's not positive, right, something like this. And here's the interval AB. Let's see what the two sides of this inequality mean. First, calculating the integral and then taking the absolute value is doing the following. Is taking this area with a plus sign, subtracting this area, right? Remember, areas where the function is under the axis contribute negative area to the integral, right? We said that. And then adding this. Do you agree? What you get may be a negative number. So for example, maybe let's revise the drawing a bit. If the area under the graph happens to be rather big, then it may be that the minus area is even bigger than the plus areas, and you might even get a negative number for the entire integral. Whatever you get, take it in absolute value. Okay, so there are cancellations of negative and positive areas. You get a number, take it in absolute value. That's this thing. What's this thing? This thing is first take the absolute value of the function. So whenever it's negative, you do this. Do you agree? And then add up the areas all in plus. That's the integral of the absolute value of the function. Do you agree? Do you agree that this is going to be bigger? Here you're just summing up all the areas in plus. Here you're first canceling them out and then taking the absolute value. So do you intuitively agree to this statement? Okay, good. Is there a way of calculating that somehow you can see? Not really, not yet, right? Okay, part 6. Yeah, I knew we were going to run out of board rather quickly, but that's okay. We'll just erase and continue. So part 6. Part 6. If f is integrable on AB, I should have had this if f is integrable on AB also on top. I'm writing this again and again. You're right. Well, too late. If f is integrable on AB and f is non-negative, f of x is greater than or equal to 0 for every x in that interval, then the integral of f is also non-negative. Intuitively, if you have a function that's non-negative, the area under the graph is going to be non-negative. This should be, I mean, I don't even have to draw anything new here. Do you agree? Everybody? Okay. And like before, when we had statements that involved inequalities, we sometimes asked, when can we replace the inequalities with strict equalities? And we saw that sometimes when we try to replace it by strict equalities, it fails. We had discussions like this for certain theorems concerning derivatives and monotonicity. Do you remember? So, is it true that if you replace this with strictly positive and this with strictly positive, you'd get still a true statement? So remark. So there's a delicate statement here, and let me formalize it the following way. If f satisfies everything in 6, so it's integrable on AB, it's non-negative if f is as in 6, and f of x0 is actually greater than 0 for some point, x0, okay?
It's between A and B, right?
Yes, everything is on AB. Okay, so you take a function integrable on AB, non-negative, and moreover, it's actually positive at a certain point, okay? Then, is it true that the integral of f is actually positive?
Yes.
Answer, no. Then, the integral of f from A to B need not be strictly greater than 0. Strictly greater than 0. Why? Why? Why is that true? Ooh, plus C. Ah, antiderivatives, I don't know what they are. Areas under graphs.
Sine and cosine.
Sine and cosine?
But then they're going to be...
Listen to what I'm saying here. Take a function that's integrable on the interval AB. Non-negative. Forget anything that's negative. Non-negative. Just like our original intuitive drawings. Moreover, there's a point where it's actually positive.
If it's not this
It doesn't need to be
Does the integral necessarily have to be positive and well? No. Why not?
You can have a removable expansion.
Right. So for example, e.g., you can have a function that maybe looks like it's 0 everywhere, except maybe at one tiny little point here where it's actually positive. Okay, so there's an empty hole here. Here's your function. Can you see it? It's 0, except at this specific point where it's really positive. What's the area under the graph?
0.
The area under the graph is still 0. So you do not get strict inequality by just requiring it to be positive at some point. You can get it if you force it to actually have area under the graph. And how can you do that?
Continuous.
Right. If you require it to be continuous, so let's write this. So let's call this remark 1. Remark 2, if f as in 6, if f as in 6 is continuous and positive at some point, then the integral from a to b of f is positive, not just non-negative. And the drawing to go along with this is the following. So now I have a point x0 where the function is positive, but it's continuous. I can't just jump here and continue at 0 intuitively. We're just doing intuitions. It's continuous. So even if I want it to be 0 on as much of the interval as I can, I'm still going to have to somehow go down and then make it 0, and somehow go down and then make it 0.
You can prove that by Eilenschutz, right?
I don't want to discuss proofs here. I don't want to discuss proofs here, because the proofs are eventually going to reduce to the definition of the integral, and I don't want to confuse you with that. But do you agree that if this is, so this is the picture corresponding to the remark 1, and this is the picture corresponding to remark 2, and there's going to be an honest area lying under the graph here if we force it to be continuous. Do you agree? Okay? So if we have a function that's not negative, but strictly positive at some point, if it's continuous, it's going to be, the integral is going to be strictly positive. Good? Everybody? Okay. These are not hard to prove, really not hard to prove, but I'd rather not do it. I think it would interfere with the flow and the understanding of the concept rather than help. Okay? Okay, so that was number 6 with some side remarks. Let's move on to number 7. So number 7 is actually a generalization of number 6. And it says the following. If f and g are integrable on AB, and f is greater than or equal to g, then the integral of f is greater than or equal the integral of g. First of all, do you agree that intuitively this makes sense? Take a bigger function, the area under the graph is going to be bigger, or less than, or greater than or equal. Do you agree? Second of all, do you agree that this generalizes 6? In 6, it was exactly this statement, only that g was the function 0. Do you see that? So if g is the function 0, you have 0 here and the integral of 0 here, which is 0, and that's precisely number 6. Okay? Good? And this property also has a name. This is called monotonicity. Monotonicity, not of the function, monotonicity, not of the function f or g. There's no statement that f or g are monotone. Of the operation of taking the integral. Monotonicity of a function was x2 bigger than x1, f of x2 bigger than f of x1. Remember? Monotonicity of the integral is f bigger than g implies integral of f bigger than integral of g. It's monotonicity of the snake. Good? Did you note that snakes are monotone? Although they sometimes look like sine waves. Oh boy, sorry. Okay, good. 8. By the way, do you see some method of calculation? Not yet, huh?
If there were one, you would have asked earlier.
Question, yes. Never mind. Okay, number 8. If f is integrable on AB, and remember that we said that our entire discussion is about bounded functions, right? Bounded. So, it's a bounded function. Let's denote by little m its lower bound, a lower bound, and by big M, an upper bound. Okay, so f is bounded. We're assuming it lives between some little m and big M. Okay. Then, the integral of f I'm going to first draw it and then write it. So leave here some room and here some space. And here's the drawing. Here's A. Here's B. And here is our function f. Some function f. There is a little m, which is the lower bound of f. There it is. It's this value here. Do you agree? In this picture? So this is the lower bound, a lower bound. And let's make it slightly more interesting. So, and there is a big M, which is the upper bound. There it is. This is big M. Good? Picture. Good? Okay. So the claim is that the area under the graph, which is the integral, that's this area under the blue graph, is greater than or equal to the area under M, greater than or equal to just this area, because there's also this area and there's also this area. Do you agree? And less than or equal to the area under big M, because the area under big M also counts this area and this little area, which are not under the graph. Do you agree? That's the statement. What's the area under little m? Exactly. M times the length of the interval. And then here, it's M, big M. Do you agree? Good?
What happens when f is negative? We don't need to
Draw it. Draw it. This is not a proof. This is just intuition. Okay? This is the formal statement.
And it's going to remain when f is negative?
I want you to see if it remains. Draw it. You have to play with these things in order. I can draw it for you. But I drew this case for you, which is the easier case. Draw it for a negative m and tell me what you see. Okay? Don't do it now. Do it later. Okay? Those are good questions, but I really want you to try it. You to don't be afraid to get your hands dirty. Okay? Okay. How would you prove this? So this is the intuition, but can somebody give me an idea of how to prove this? When I say prove this, I assume that you already know everything that came before it. So you don't have to reduce to the actual definition. You can use any of the, we had 7 theorems in now, and we had the statement about continuity and monotonicity previously. Can you actually prove this? Claim, yes, you can, and claim the proof is actually going to fit without reducing the font size in this area.
By number 7.
Right. Use number 7. How do we use number 7? Well, saying that f is less than m, okay, so let's do the other side. Saying that f is greater than m, take g to be this m, the constant function m, right? If f is greater than m, then the integral of f, so by 7. F greater than or equal to m implies the integral of f from a to b is greater than or equal to the integral of the constant m from a to b. That's 7. Do you agree? And what is the integral of a constant? That's one of the 3 things we did calculate. It's m times b minus a. So that's this part of the inequality. For this part, you just have to take f as m and g as f. Right? Good? Everybody? Smile. Thank you. Okay. So I'm going to write, okay, you have to do the same thing but I don't want to write it again. It's just repeating the same argument. Okay, so we know this. This is already slightly closer to being able to calculate. We still can't calculate, but we can somehow have an upper bound and a lower bound for the integral. But it's a rather not such a good bound. Saying that so it introduces a huge error. All of this thing is going to be an error when we calculate the upper bound, right? So it's not such a good way of, doesn't help us calculate, it helps us do estimates, and they're rather lousy estimates. Do you see that? Yes?
But this is going to hold all the time for definite, no? Because
What do you mean all the time for definite?
in a closed interval, it's always going to have an upper bound and a lower
Right,
bound.
right. This is a theorem. That's the statement. This holds for any function on AB. Okay, I'm just saying it doesn't help us. It's an inequality, not an equality, and the estimate you get by using these inequalities is rather lousy. Okay, you don't get the actual. It's not like, like you say, it's like saying that E is between 2 and 3. It's not really telling you what E is. Okay, good? Okay, number 9. Let's do number 9. So number 9 also has a name. It's actually called the intermediate value theorem for integrals, for snakes. And it says the following. If f is, here we have to strengthen the assumption a bit and actually assume that the function is continuous on AB. That, of course, implies that it's integrable. That was a theorem that we had. Any continuous function is integrable, right? Okay, so if it's also continuous, then there exists a C in AB, that's the intermediate point, such that the integral from A to B of f equals f calculated at C times B minus A. Let me first convince you why this is true. So let's go back a second to the drawing, the intuitive drawing corresponding to theorem 8. The statement here was that when you have your function and it's between little m and big M, then the integral, the area under the graph, is bigger than the area under little m, that was this value, and smaller than the area under big M, which is that value. That was the statement of 8. Now the statement is that there is actually some value C lying here between A and B, such that the integral, maybe let's take another color. The integral, the area under the blue graph, which is this plus these two areas, actually equals the area. So let's say this is the point C. I don't know if I was very accurate. This is f of C here, and the area under the blue actually equals precisely the area under the orange, f of C times B minus A. Somehow, the plus and minus areas, by doing this, cancel out. Okay, that's the statement. Let's formally prove this one. I want to formally prove this. And the proof is gonna, the core idea in the proof is gonna be the intermediate value theorem for functions, which require the function to be continuous. That's why we need the continuity here. Okay? So let's prove it. So by 8, we know that m times b minus a is less than or equal to the integral of f, which is in turn less than or equal to m times b minus a. This was number 8, right? Let's divide throughout by b minus a. Let's divide by b minus a. So we get, when I divide by b minus a here, b minus a is a positive number, so the inequality remains the same, is less than or equal to, so I'm going to write this again, integral from a to b f of x dx divided by b minus a less than or equal to m. Do you agree that this is what I get? Yep. Now, if you go to the zoo, not the regular animal zoo, the mathematical zoo, where you have all these mathematical things living in different areas, safari, they're free to roam, okay? And you have an area where you find sequences, and an area where you find just numbers, and an area where you find functions, in an area where you find, I don't know what. Where would you find this thing? What is this thing? No. What kind of mathematical animal is this thing? Very good. Who said that? You're right. This is a number. The integral from a to b of a function is a number. Right? It's that I, remember? That the Riemann sums approach. It's the area under the graph. It's a number. Do you agree that this is a number? That's crucial. An integral of a function, a definite integral of a function, is just a number. Does everybody agree to that? That's important. When I divide it by b minus a, it's still a number. This is a number, though we've written it in a somehow confusing way. This is just a number. What number? Between m and little m. What are m and little m? These are values of a function. And the function is continuous, so these m and little m are actually obtained. It's a continuous function on a closed interval. It actually has a maximum and a minimum. Right? Does everybody agree? So this is some value between the maximum and the minimum of a continuous function. By the intermediate value theorem for continuous functions, there exists a point C. So let me write by the intermediate value theorem, which we wrote in short IVT, the regular one for continuous functions. There exists a C such that f at C is precisely this number. That was the intermediate value theorem. Take any y0, y0 between two values that the function obtains. There's an x0 at which f of x0 equals that y0. Remember that theorem? So there's a C at which f of C equals this thing. Did everybody follow? Questions? Yep.
Can we prove this by making a new function g, which relates the area to the y value between m and m? And saying
M and M is good. I like M and M's. But what? Say that again.
making a new function
Define a new function g.
of the area as a function of the y value.
The area as a function of the y value.
And that function is between little m and big M.
Okay, so I don't know precisely what you mean. Okay, so maybe I'd be happy to see what you mean later during the break. Okay, but remember, if you think of the function as a function of the y value, it's no longer a function. Right? Look at it like this. It's no longer a function. So I don't know exactly what you mean. Maybe you mean something correct, but let's talk about it later. Okay? I want to. So is this clear? This is really the intermediate value theorem for a continuous function, with this being the value that I want to obtain. And I know I can. And now multiply by b minus a again, and you get precisely this. Do you see that? Good? Do you now see a way of calculating integrals?
Yeah.
How?
Oh, I don't exactly understand. I see a way.
You see a way where?
That we have value now.
We have a value, namely this value.
Yeah.
That exists.
Right, exactly. This still isn't a solution to our problem, because the only statement here is there exists a C. What is that C? You don't know. This is an existent statement rather than a way of calculating. So all you know is that it actually equals b minus a times this value, but you don't know what this value is. Do you agree? We're still not there. Good? Clear? So this is... We're going to see how useful this is. In fact, we're going to use this specific theorem in proving the fundamental theorem of calculus, but this by itself is still insufficient for actually calculating. Clear? Okay. Last theorem in this list, number 10, is going to be the following. So it's not that this list is just for you know, for putting a V that we saw them, now we can move on. We're going to use all these facts. We are going to use them in proofs and in calculations and everything, but they're still not enough for doing the calculation. There's still a missing ingredient. Okay, number 10. If f is integrable on AB, and let me call it f tilde rather than g. F tilde is another function, differs from f. So by saying I'm calling it f tilde, I'm saying, well, it's related to f. It differs from f at finitely many points. So you took f and you changed its values at 1,700 points, okay, but only finitely many. Then f tilde is integrable, and they have the same integral. The integral of f equals the integral of f tilde. So by changing a function at finitely many values, you don't change the area under the graph. Okay? And a way to kind of think of it is the area under a point is 0. That's how we defined it. Remember? The integral from a to a was 0. So if you kind of change it finitely many points, you're introducing changes that don't really affect the area. If you want to affect the area, you have to change it on intuitively, on an interval. Okay, this is just intuitively. You have to change it on an interval, and an interval has more than finitely many points. Right? So that's the statement of this thing. Okay. So I think this is a perfect point to stop. So let's have again a 10-minute break, and afterwards, well, 10 minutes break.